Hey everybody, welcome back to another video on Feynman integration. Today we'll be evaluating this integral from 0 to infinity of e to the negative x squared cosine x dx. Our first step, like always, is to create a function of t closely resembling that integral. In this case, I just put a t right there in front of that x to give us this. F of t equals the integral from 0 to infinity of e to the negative x squared cosine x dx. Note that f of 0 is equal to the square root of pi over 4, because if you plug in 0 for t, you will get cosine of 0, which is 1, leaving you with nothing but the integral from 0 to infinity of e to the negative x squared dx. That's half the Gaussian integral, which is equal to the square root of pi. So I just wrote that as the square root of pi over 4. Next thing is to evaluate f at 1 to get I. That will be our final step. If we can find a good representation for f of t, that's not this, and then plug in 1 for t, we will have our original integral. So the next step is to use the Leibnitz Rule written up there to evaluate, to take a derivative with respect to t of f of t. Using the Leibniz rule, we know that f prime of t will be equal to the integral from 0 to infinity of the derivative with respect to t of the integrand. And that's written right there. So we have f prime of t is equal to negative integral 0 to infinity of x e to the negative x squared sine tx dx. I actually wrote out the steps involved in evaluating this integral just to pad the runtime and to fill up the whiteboard space. I used a method made popular by Black Pen, Red Pen. I will link to his video explaining this method. It is the DI method. And Black Pen, Red Pen made this method very popular for integrating by parts. It's much quicker and it's just more organized, but you get the same thing. So here's my DI setup written right down there. The first step in using the DI method is to just, however many times you think you're going to integrate by parts, just write a plus, minus, plus, minus, plus, minus, all the way down. In this case, I only had to write it twice. And then what you do is you determine which part of the integral you would like to differentiate in your integration by parts. And in this case, I chose the part negative sine tx. Negative sine tx. So we'll be taking a derivative of that. And obviously, for the part we will be taking the integral of, it's just what's left. So that would be negative x e to the negative x squared dx. And I wrote it a little bit different right here, but it's the same thing. I wrote it as negative 1/2 negative 2x e to the negative x squared. And I wrote that to make it easier to do a u substitution. Our u sub would simply be that u is equal to negative x squared. And then we just have our du right there. So that's why I wrote that way. So anyway, when you take a derivative of negative sine tx with respect to x, you get negative t cosine tx. And when you integrate this, you get negative 1/2 e to the negative x squared. So we know that we know that if we evaluate this integral, we will get this times this evaluated between our bounds of integration, which is 0 to infinity. And the whole thing right there will evaluate to 0, because we'll have, let's see, negative times a negative is a positive. So we have 1/2 e to the negative x squared sine tx evaluated from 0 to infinity. If you plug in infinity for x, it goes to 0, because e to the negative infinity is 0, and anything times 0 is 0. Also, if you plug in 0 for x, the whole thing will go to 0 as well, because sine of 0 is 0. So that whole thing just cancels out, leaving us with negative, 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 which is negative. T over 2, that's the T over 2, integral 0 to infinity of e to the negative x squared cosine tx, sorry, dx. It's important. And then we notice this right here is simply equal to 1/2. Oh, no, I'm sorry. It is not equal to 1/2 f of t. It's equal to t over 2 f of t. See, this is our f of t. And this is also our f of t, just multiplied by t over 2. So that can simply be written f prime of t is equal to negative t over 2 f of t. Making the substitution y is equal to f of t, which is not technically necessary. I just like to do it because when I'm doing differential equations, I like to use, I believe that's Newtonian notation. I always get them confused. One of them is Leibniz notation and one of them is Newtonian. But I like to use the d something over d something else. So I set y equal to f of t. So rewriting this equation right here using this substitution will give us dy dt, which is f prime of t, is equal to negative 1/2 t times y. Then multiplying both sides of this equation by dt, which is legitimate. It took me a while to wrap my head around that, but it's a legitimate thing to do because this is nothing but a ratio. So anyway, yeah, multiplying both sides of this by dt and then dividing both sides by y will give us, and then integrating both sides, will give us integral 1 over y dy equal to negative 1/2 integral t dt. Evaluating both those integrals will give us that the natural log of y is equal to negative t squared over 4 plus c. Taking both sides of this as an exponent on e, we get y is equal to c e to the negative t squared over 4. And a lot of people kind of struggle with this c right here. I know I did when I first encountered this, but the reason for that is that if you take both sides of this as an exponent on e, you'll end up with e to some function of t plus c, which is the same as e to some function of t times e to the c. And since c just represents an arbitrary constant, e to the c also represents an arbitrary constant. So we just bring that c right down. Of course, it's not really the same c, so I wrote this c as c sub 1, but that's an arbitrary constant, so is that. So we have that y is equal to c e to the negative t squared over 4. Also remember that y is f of t. So if we evaluate f of t at the point t equals 0, we get square root of pi over 4. So we know that 0 is equal to c, I'm sorry. We know that the square root of pi over 4 is equal to c times e to the 0, which is 1. So we know that c is equal to the square root of pi over 4. So now we have our final expression for f of t, being that y, or f of t, is equal to the square root of pi over 4 times e to the negative t squared over 4. Then plugging in 1 to get I gives us I is equal to the square root of pi over 4 times the square root of e. And that's That's great. I think that's wonderful. You have square roots inside of square roots. You have pi. You have e. The only thing that's missing from that is like the golden ratio or something. I mean, that it's just crazy how those numbers show up so often. But anyway, hope you enjoyed that.